My name is Daniil Kargin. I'm a chemistry student in NTU Singapore, and I have participated in the International Chemistry Olympiad 3 times, 1 bronze medal and 2 silver medals. And today I'm going to teach you a bit about chemical and general thermodynamics, especially the reason people hate it and the reason you actually should love it. So yeah, first of all, a small introduction into what is thermodynamics, what are we even talking about all this time, and why people hate the thing we're talking about. So the thing about thermodynamics is that unlike all the other branches of physics that you have encountered so far, and most of you in your high school have probably heard about 2 types of physics, which is classical mechanics and classical electromagnetic theory. Nothing else. Am I correct? Approximately, yes. Okay. So the thing about classical mechanics and electromagnetic theory is that it kind of just makes sense because it talks about real objects. So you can take, okay, force is something you use to pull an object. Or electromagnetic field, you can still talk about some sort of attraction because they're like charges. You can imagine it. Thermodynamics is really abstract. So you cannot talk about Gibbs energy, you cannot measure, you cannot see Gibbs energy, you cannot measure entropy. This is why the subject is weird. It's really abstract. And you have not seen anything as abstract as thermodynamics before. If you're talking honestly, you can make even higher levels of abstraction from stuff like electromagnetic theory and classical mechanics. But at least in school, they don't teach you stuff like movement of a point on a curve in 6-dimensional space that describes the equation of motion due to the point choosing the line with the smallest integral of energy. They don't care about this. Neither will I. So, a thing about thermodynamics, why everyone hates this, is exactly this. It is abstract. It is talking about some abstract energy conversions. It's not talking about real energy that you can measure. But on the same time, it is used to describe real objects. So your reaction, your engine, anything, which is why it's kind of counterintuitive. You cannot say it's like quantum mechanics that like there is a wave function and you can't even measure it. And if you try, it does not work. It's not this way. You can see it with your eyes, which is why it's weird. But yes, the thing why thermodynamics is so nice is exactly because it's abstract. We never ever mention a single system when we talk about laws of thermodynamics. It means that if we say that a constant temperature and pressure Gibbs energy determines the spontaneity, we don't care what are we talking about as long as the Gibbs energy of, I don't know, your reaction of an engine, of an explosion of the car, as long as it decreases under constant temperature and pressure, it will show that the reaction, the process is spontaneous. And this is why we actually love it as chemists. We don't need to know anything about the reactions we describe. We just need to know the general laws. So knowing this, we will quickly begin introductory concepts and points that you need to know so that we understand each other and we understand thermodynamics. And for the people who are watching, there are the lecture notes you can print. And I suggest that you print them and fill them out together with everyone else while we're going through the lecture. If you have any questions, the people who are here can ask. If you're online and you're from the Latvian team, you can message me directly. And if you're watching it later on, I don't know what to do. So yes. First of all, we have to say the scope of events that we concern in classical thermodynamics. And especially in this case, because it's a chemistry preparatory lecture, we're going to concern the 2 main advanced difficulty topics of this year preparatory set, which is thermodynamics of chemical reactions at weird conditions and electrochemical cells. Again, I'll mention once again, for the, I think, only time in this lecture that we're talking about classical thermodynamics, so we're not talking about separate molecules, we're not doing any statistics today, because it's not covered in the syllabus and I don't see point to torture with integrals because of this. And now let's just talk about something that our science of thermodynamics actually concerns about is a system. So what is a system? A system is just something that we care about how it behaves over time. So the system that we're concerned about in classical thermodynamics is just such an aspen. So it's just something, some system. We don't know anything about it, and we do not need to know. We just need to say that it is behaving as thermodynamics suggests, as long as it's large enough, so it should be large. What do I mean by large? I don't mean the actual volume. I don't mean the actual size. I mean the amount of independent particles that can move inside it. Why is this needed? It is needed because this way it actually correlates to the statistical mechanics you can show. Then you also need to find some way to distinguish where the system begins, where it ends. So there should be some boundary. Well, because the systems usually exist in our three-dimensional space, it's usually some surface in 2D, which covers a 3D space, and we usually call it a boundary. So this is why also usually a system has some defined quantity that describes it. So there is some parameter we can use to describe both the internal state of the system and the external state of the system. So because I already mentioned, you can probably somehow distinguish where the system begins and where it ends in our space. There should be some way to characterize where the system is. And people usually just use volume, but you can use whatever else. Okay, does it make sense so far? Do you get what is the system? Okay. So you see that the problem about the system. I already said, okay, we need to somehow describe it. But okay, let's say like this. So you studied classical mechanics, right? What do we use to describe a particle in classical mechanics?
Mass, speed,
Coordinate. Yeah. So it's generally sufficient to just give coordinate of time as a function because velocity is derivative, force is mass times second derivative, etc. Makes sense, right? Okay, and now I'll ask you a simple question. I want to describe this system. It has 10 moles of chemicals. Is this viable? So I need to give 10 moles of such equations for every atom in the system. And I'm not even talking about quantum mechanics that say it's not possible. So you see, there is a small problem when we talk about a mole of compounds, a mole of particles. This is why we actually have to introduce something called a macroscopic variable. So the word macro itself should suggest that it's used to describe something large. So this would be a microscopic variable. It describes one particle you can look at under the microscope. It does not describe all this block of iron or something. So there are macroscopic variables are just some variables that you can use to describe the system. So obviously the quantities that you're using to describe the system are somehow related. For example, let's just give the simplest example. I know we have temperature and volume, and we have the energy of the system. So we say, okay, energy is probably some function of all the other variables. Makes sense, right? Okay. This is the general idea behind classical thermodynamics. We just say it's probably doable this way. We don't say why. We just say you can. So then we need to figure out what are the types of variables, quantities, and physical units you can actually deal with. And there are two, which are the ones that are actually important. There are intensive and extensive quantities. There is an intensive and extensive quantity. Okay, what's the difference? Well, you can see from the name, this one has in, this one has X. So this one is somehow inside of the system. So the simplest example would be something like temperature. What's the thing about intensive quantities? You can use an intensive quantity to describe some point in the system. I can say, this point has this pressure. This point has this tension. This point has this energy, or something like this. So you get the idea, like this energy density or something. And we have extensive variables. What is an extensive variable? An extensive variable is a variable that can only be defined for some part of the system. So I cannot say this point has volume, or I cannot say this point has total charge. We can only say there is total charge of a part of the system. There's a volume of this part, there's the volume of this part. I cannot say entropy of a point, I can say entropy of the whole system, or entropy of this part. So do you get the sense what it is, right?
Kind of.
Kind of, okay. And for intensive variables, there's also one more important subtype of intensive variable that is called force. Okay, now let's just think about a bit about how it works in our classical example. So when your object, your car or something is in equilibrium, what happens to the force that acts on the car? It is zero, right? So if the forces are not the same, the car is moving in some direction. It's not in an equilibrium state. The same is true for chemical and thermodynamic quantities. So if we say a quantity is a force, it means that if the system is in equilibrium, the value of this exact variable is the same. The simplest example is temperature or pressure. Because let's think about pressure. If the pressure is different in two sides, the system will just physically move until it equalizes. Because pressure is mechanical force over the surface area where it's applied to. So yeah, it's the simplest analogy why it makes sense. Okay, does it make sense so far?
Yes. It's only for the intensive variables.
Well, force is a type of intensive
Yeah.
variable. So
So it's different.
extensive variable is just some variable you define outside usually. So like volume. Intensive variables are variables for one point of a system. So the simplest analogy is that I cannot say volume of a point. I can say temperature of a point. That's the difference. Okay. Yes, obviously there can be dependent and independent variables as well. Independent variables are the variables we can choose to change as the person who does the experiment. So for example, I know if I want to measure heat capacity of temperature, I can just change temperature and look how the system responds. So temperature is independent, everything else is dependent. Okay, another thing you need to know, intensive variable. For an intensive variable, there can be a jump in the system. This is why I say not all are forces. The simplest example we can say is, for example, this one is ice, this is water at equilibrium. So it's like half melted ice. And we see that we look at the mass density. Okay, first of all, is it intensive or extensive density? Can you say density of a volume? Can you say density of 1 kilogram?
Not really.
So it's intensive because you can say density of this part, density at a point, or density of everything as a whole, if it's the same. But if you look at this case, the densities are different, right? Ice floats on top of water. So but it's at equilibrium. So you see density is not a thermodynamic force in this case because it jumps. Here the density is 1 and here is the second. So it just jumps. And this is what lets us to distinguish different phases of a system. So when a system divides into two parts with different values of this variable, they're called phases. And you've heard about them when you talk about like boiling and such processes. Yes, okay. And you say if a system has no phases, it is homogeneous. And if not, then it's heterogeneous. We're going to also mention a thing called thermodynamic contact, which is we have two systems, and we want to say those systems can exchange some variable. And it happens via a thing called thermodynamic contact, which can happen in three different ways. First of all, it can be some field, which is, for example, electric charge or volume. or pressure, those sorts of like things you can actually quantify with some mechanical work. So change of mechanical energy. And there's heat. We don't know anything about heat. We haven't talked a single word about heat in classical physics. There is just no analogy. And we just say in thermodynamics heat exists. We don't say why, we just say it exists. And also diffusion, which is particle just going out of the system. So the three types of thermodynamic ways system can exchange the energy between another system and the first system. And we also defined three types of system, which is isolated, adiabatic, and closed. So isolated system, it cannot exchange any energy. So the energy you put in stays forever. It's a perfect case for a system that just does not do anything except stuff that happens in itself. There's adiabatic system which can do anything but heat. And there's the closed system that can do anything but matter exchange. And usually when people imply adiabatic, unless said otherwise, it's also closed. Mention 5 different variables to describe a system that I didn't mention yet or didn't mention in the notes. And you have to say, are they intensive, extensive, or forces?
Entropy.
Entropy, okay, nice one. Entropy, yeah, it's extensive. Okay, any more ideas? We need 4 more.
Number of modes.
Yeah, amount. Is it intensive or extensive? Okay, any more ideas?
Time.
Time is a weird one. So the thing about time, yes, it is an extensive variable, but in our case, we'll just not mention time at all because it kind of contradicts the things about equilibrium. So we're going to talk about not equilibrium states if you mention time, but we will not do it as of now.
Even enthalpy.
Enthalpy, yeah. Is enthalpy intensive or extensive?
It's extensive.
Why?
Enthalpy is
Can you say enthalpy of all the system? Well, yes.
kind of
Yeah, it doesn't jump, so yeah. Okay. Any more ideas? Get the next question.
the potential.
Potential chemical or electric? Let's write both. So this is electric potential and chemical potential. Are they intensive or extensive? Yeah, so this is extensive. Wait, I forgot to write here. This is extensive. Those are intensive. Okay, and what can I say about those two intensive variables? Do they have to be thermodynamic forces? Yes, so they're also forces. Okay, we've done the first problem, and now there's another problem, which you can also try out, which is just more of a discussion question. So how can we experimentally make a system isolated?
The cover is maybe usually something insulated.
Well, okay, let's first of all, it has to have no sorts of to exchange energy, right? So insulated will help about insulation will help against heat. Okay, then we also have to ensure that it has constant volume because it cannot expand, change its energy by expanding against the pressure. What also?
Better say.
Yeah, so you have to seal it. Okay, yeah, and you have this box which is like in a non-changing constant field, so probably you either have no electric field or just a constant one. So it cannot change energy. So the energy you put in is the same. And the question is, can you measure any quantity of the system experimentally? In this case, when it's in equilibrium?
Not really.
Why?
Because to measure it, you have to disrupt the insulation and
Well, you either have to disrupt the insulation, or let's imagine, I don't know, I have a Bluetooth probe that can measure pressure. But then I have to include it in the system. So I have to include something that can interact with the system for the pressure to equalize. So it stops being isolated at this point. So the problem is that it kind of looks the same as in quantum physics, that we cannot measure a thing without changing the state of the system. Okay, now let's talk about the laws of thermodynamics, the stuff that actually matters for us. Okay, so The laws of thermodynamics, they're quite weird for us, but I'll just briefly mention them, why they work, how they are, and everything else. So first of all, there's the law number 0. The law number 0 is just a thing that was actually, you might first ask why it's number 0, not number 1. The reason is people first invented the laws number 1 and 2, and then realized they need number 0 for 1 and 2 to work. So they had to patch it up this way. By the way, if you are curious about history, the majority of works on the thermodynamics as we know it today was done by no one other but Dr. Josiah Willard Gibbs in the late 1890s. So yeah, he quite frankly deserved to have Gibbs energy called after him. Okay, so zeroth law. The zeroth law talks about two things. What is equilibrium and what is thermal equilibrium? So first of all, general equilibrium. We say, okay, there are quantities and a system can probably change the quantities over time, somehow. So I know we can say, for example, I know temperature might go like temperature. Let's just draw a graph, it will be simpler. Temperature, time, right? So it might be something like, this. Right? Just an example of how it might look like. It's probably not the way it looks like in real life, but who cares? The thing is, if we leave it go long enough, we say that all systems reach this state, which is called equilibrium. The thing is, there's some average value, and if T deviates of this value, it's not by a large amount, which is called random fluctuations, which are a consequence of statistical physics once again, but we'll not talk about this today. So yeah, we just say that after time, it will just reach this equilibrium state. And even more importantly, if you don't do anything, it will stay in such a state forever. So this is the reason, by the way, why I said we don't talk about time in thermodynamics. We just say time is long enough so that it's like here. So we have before and in equilibrium when we talk about time as a thing in thermodynamics. At least in equilibrium chemical thermodynamics we're concerned about today. Yes. So the other thing we have to say that we have two systems, A and B. And we say, okay, they're in equilibrium. So they're in equilibrium with each other. And at the same time, A and C are also in equilibrium. And because of this, those two have to be in equilibrium also. And this is called transitivity. If you think like this, you probably noticed that in fourth year maths, when you talk about this equals sign or the less sign and greater sign, they also say, okay, if A is more than B and B is more than C, then A is more than C. It's the same concept, but we just use it for the equal sign here. So we can say the equilibrium is sort of equal sign for your equation, but not really. Okay, and the idea, what it concludes to is also we say that if A as a whole is in equilibrium, then we can split it into as many parts, and all those parts are also in equilibrium. Makes sense why, right? Yes? Because we say if this and this has to be in equilibrium, then you can split it once more. Those are in equilibrium, those are in equilibrium, those are in equilibrium, those are in equilibrium. So everything is in equilibrium with each other. So the total system also has to be in equilibrium somehow. Because otherwise there would be some process that would shift it out of equilibrium and go back. Makes sense. Okay. And then we also say temperature. So temperature is a weird one in thermodynamics. Temperature, we just say it exists. This is what is called a postulate. We just say it exists. And we just say it exists in such a way that if two bodies are in thermal equilibrium, they have the same temperature. And we also then would say that T is greater than 0 because it's convenient. Okay, makes sense, right? Okay, and now I have a bunch of proofs, so I want one of you to come and suffer. The first proofs are easier, then it gets harder. So who of you wants to do the next proof? So I'll voice it for the people who are watching. So the proof is to prove that temperature has to be intensive and it has to be a thermodynamic force. Okay, I give you a hint. So try to think, you know the zero flow, right? And we just said that if a system is in equilibrium, its parts are also in equilibrium.
Yeah.
So you could draw something for an analogy if it helps. Draw a larger circle and just split it into two. Okay, two is enough, I would say. But you can take more, but who cares? Okay.
Okay, so if the entire system is in equilibrium,
Yes.
then we can split it in as many parts as we wish.
Yes.
And in each part, it will be in equilibrium with another part.
Yes.
So
temperature has to be the same.
Temperature has to be the same, and we can take an infinitely small part of.
Yeah, you can take whichever point, so you can literally choose whichever partition, right?
Yes.
So you can select any point as like part of a separate system if you want to.
Yes, and
Yes.
it will be equal to any other.
Yeah. So at least you said okay, because we can choose those two parts however we want to.
Yes.
This would apply for any point, so it's intensive, right?
That's
okay, we have proven the first part, and now thermodynamics force, as you said, because you can choose whichever two parts, it has to be the same for whatever 2 points you choose, basically.
Yes.
So it has to be
a force.
A force, because it's in equilibrium, the same across all the system.
Yes.
Okay, proof concluded. Congrats. You see, proving is not hard. Give it
This one.
from here. Okay, next one. Anyone, you can probably just say. So we need to invent some experimental device that can measure temperature, and explain why it works. So basically, we could just say why your normal thermometer actually works the way it's supposed to work.
Because it's a part of the system in question.
Well, let's say like this. What is the thermometer to begin with? So like I know, like imagine there is this thing, and I take my probe and I stick it inside, and the question is, how can I understand the temperature reading from the probe? And how can I understand that the probe does not lie? So, okay, let's first begin on the first part, how we can measure how the temperature affects the probe. And here I would suggest we need to remember how the quantities behave in the system.
Well, temperature affects the energy of the molecule.
Well, it affects, so we can say it can affect almost any quantity.
Yes.
We don't know about the energy of molecules, but we can.
The volume.
Yeah, we don't know. That's the thing. We don't know. But we can say that there is some quantity. It might be like, density, or it might be the height of the mercury line in the thermometer. And we just say, okay, we know the function, how it behaves of temperature, right? So then we can get the temperature knowing the value of the function, right? Because you can solve for temperature. Energy is just convenient so that we know that so we just say in thermodynamics that energy is 1-to-1. So there is no such case that one energy has two temperatures corresponding to it, which is very convenient for us. But like, I don't know, for something like density, it might not be the case. So yeah, we just say it works this way, and then we need to say why it actually measured the temperature of the system and what are the requirements so that it says the temperature of the system. Mm-hmm.
Well, because if it reaches equilibrium.
Yeah, it reaches equilibrium, so it has the same temperature as the system when it reached equilibrium. And if we want the temperature at equilibrium to be as close as possible to the initial temperature before we added the thermometer, So what has to be about the thermometer? It has to has
minimal
heat capacity.
yes.
Yes. So it needs to take as little energy from the system to reach an equilibrium. Do you get why, right? Because otherwise it will just drain out all the temperature to balance out. Okay, this is the zero flow. So zero flow just literally says, okay, equilibrium exists and there is temperature. And now there's the first law. The first law, it's a weird one because it totally makes sense, but at the same time it doesn't. Usually people get stuck somewhere in the middle of the first law because they don't totally understand the idea. So first of all, we just remember that the internal variables of a function. So again, a reminder what is internal, external. Externals are the ones we define. So like if I can set up the temperature the way I want to, temperature becomes external. Because it's not reached somewhere in the system. I can set it. This is why it's external. So we just say any internal variable is somehow dependent on the external variables. Because if it's not, we just don't know anyway how it behaves. Right? Makes sense. Function of t and everything else. I'll write external variables using the letter A. A. Okay, so I'll just write this way because it's convenient for me. And we also say there is something that is called internal energy. We just say it exists at the moment, right? What is internal energy? It's the energy that we have accumulated in the system. And we say, okay, it's probably the same internal variable, so it has to be a function of temperature and all the other variables. Makes sense. Okay. And then we also want to add one more thing. We just say it is this way. We don't need to prove it. We just say that the U over the T for all A is greater than 0. This notation means that I don't change all those external variables. So I only care about temperature. I take the derivative while the rest is constant. So I just look at the temperature slope. And I say it's always greater than 0. So if I add temperature, I increase the energy. Okay. And then I can do the same for the conjugate variable. What's the conjugate variable? We'll go back to it. But I say, okay, there's some other conjugate variable which I'll call A. I always forget. I'm sorry, guys. I always forget I cannot do it. We say there is a large A, which is the same function of the A1, A2 to AR. I say there are times different external variables. We can just say this is called thermic state equation. This is called caloric state equation. You don't need to know this. I just say it is this way. So now we can just say what is the first law. So we say internal energy is something which is an extensive variable that adds up as parts of system. It is conserved and it is transferred via thermodynamic contact. So basically it's the law of energy conservation, just written down in such a weird way. And now let's think a bit about how energy changes in classical physics once more. So how do you change energy of a system in classical physics?
Apply work.
Apply force. Work is force times distance. But this is correct. So you said work is force times distance. So we say we need to apply some force, which is minus force. So it's force times distance is energy, right? Okay. And then we can say there's probably something similar in thermodynamics, right? Well, this is our coordinate. Kind of looks similar, right? We have energy expressed from them. So we can say, okay, and let's just call this thing a conjugate force. So it's the derivative by this. So it's how much the energy changes if you change A by some value. And the minus sign is again for convenience, just so that it looks the same way as in classical physics. Okay. And then let's just think this way. So the heat and the energy, it can go via some types of thermodynamic contact, right? Okay, I'll have this forever, I think. So we have some kind of thermodynamic contacts that can exchange energy. And we say that the total energy is conserved. So what can we say? We can say that the energy that goes inside here should stay here, right? Does it make sense? And this is why we say that, again, we just say it is this way, we don't prove it. For now, we just say it is this way. That's the weird thing about the laws of thermodynamics. We just say a lot of things. It's kind of the same as like in geometry, you say the 5 points of Euclidean and then you just do the math from it, which is pure logic. So we say that the change of energy equal work plus heat. Because we already said that work is corresponding to external variables and heat we don't know. We just say it exists. And the sign here depends on who uses and who writes the book. I'll use the minus sign so that it's convenient further on. Atkins uses a plus. Why? Because in this convention, it means work is the work that the system does. If it's a plus, it's the work we do on the system. You get the difference, right? You just need to be careful about the sign if you do it, but you'll not have to worry about it at least this lesson and in this Olympiad. So, but do take note, like for example, in IChO 2015, they did look at the signs and they actually asked about it. So just for you to know. Okay. You asked me why I chose this letter delta instead of D. Well, we know that energy is just energy. It's just difference of energy. So two states, energy is the same. But the way you got this energy change can be whatever. For example, if we just call, like, for example, we already said that the work is proportional to the A, external variables, right? But we can technically change energy while the external variables don't change, right? So this term just comes up to zero, and it's just thermal energy. Or you can do the same energy change in an adiabatic system, so you can just get rid out of this part. So you see, there are lots of ways you can write it down. This is why it's quite weird. Yeah. Okay, now another question. You see, now the questions I can just ask them, you don't have to prove it. So is there any way to experimentally measure the absolute value of the internal energy?
No.
Yeah, there's not such a way. Because you see, we only talk about the difference. So in the end, when we try to integrate, we will end up with plus constant all the times. And it's a problem in all classical physics if you see this. Like if you remember potential kinetic energy from 9th grade, you also have to choose some point where it begins, where you say energy is zero, if you remember. It is fixed by Einstein's relativity theory, where you say the constant equals mass times speed of light squared. In relativistic non-quantum mechanics, but we're not talking about this today. So not today. And then let's think like this. So we have this process. There's this value of AI. And for example, from this side, I'm just changing AI. So makes sense how, right? And what happens with the conjugate? So conjugate with the force. When I move it some way, it looks like in this part of the system, it is not the same because the system has not reached equilibrium yet. Makes sense, right? And you're kind of supposed to leave it long enough so that it reaches equilibrium so that we can continue. What happens if we don't? We can just push it straight up, and then the value here begins the same. So it's the same one as it was initially outside, right? We just push it all the way. Makes sense. Yes? So this is called irreversible process. Or there is another type of process, the process where we leave it to reach equilibrium. So we do this change slow enough so that the system is always in this equilibrium amongst itself and with the rest. And this type of process we call quasi-static because it's a static process. So all the points of the system, it is in static state, so it's an equilibrium. We also call it reversible process due to this exact reason, so that you can just revert it back and nothing changes. Okay? So it is also quite an important word to remember because I'll just say it too many times over this lecture to be comfortable with. And now let's think this way. So then we can say that because du over dI is minus RE, right? This case plus, because I'll just leave it here in the minus sign. What do you see here? You see that in this case, delta U would be supposedly AI times AI, large times small, right? But what happens if it's not at equilibrium? Then this value is the same all the time during the process, right? And it's equal to this one because it didn't have time to reach equilibrium with the inside. Make sense? Like why? I have the external, not internal force. Because I push with some force, and if I push fast enough, the force inside just does not have time to reach equilibrium. And so in this case, I would get the equation of this. Wait, what did I write? Like this. So I change AI and I put external. And it's important this external right now. Because I can choose whatever external quantities and it will change the heat. You see why, right? And what happens, this is general formula, so it's not reversible. And what happens if the process can revert? This one is the same as the internal one, right? And is there more than one way to perform the process reversibly? Well, not really. This quantity has to be the same if the initial and the final state are the same, right? So in like this case, the heat will be always the same, right? You see why? Or do I need to explain a bit more why? So like in this way, I can choose whatever external conditions and whatever values for this zero condition outside, right? And the difference between this one and this one will be always different according to which ones I choose. But if I choose such a case so that they are all equal to the equilibrium ones, there's only one equilibrium state. So all the states are the same in this reversible stage. So actually I have to say that in this case, the U equals by Q E. So the thing here is that you see I forgot the zero. And it was intentional because I say in a reversible process, it's the same as outside. And now let's just look at a fun fact that some of you are going to suffer. But let's think like this. So if we have a non-reversible process, the work we have to perform to conduct the process. So we have to put in some work from outside, right? My question is, do I need more work to do it if it's reversible or not, and why?
Or if it's reversible.
Well, no, the work needed. So like I need to put in work. In the slides, it's a bit weirdly written. I'll explain why. But let's look like this. So imagine I'm putting work from the inside. If not, just flip the signs, the logic is the same. So a system is not at equilibrium, right? So there is some force difference. We need to counteract with our external force, right? So we have to apply a larger force, right? So do we have to put in more or less work in this case?
More.
More. Yeah. So the work, and now let's think the other way. If the system does the work,
They have to apply less.
then the system has to first of all counteract this imbalance and only then do the work. So the actual work the system has to do itself is less. But if we do the work on the system, it's the other way around. So we say that if we do a quasi-static process, if the system performs the work is the maximum amount you can achieve. If we perform work on a system in a quasi-static way, it's the least amount of work we need to use to get this result. And now I have one problem that first of all, closed system, right? For the closed system, I have already written it down. You can just copy it down. The only thing you need to remember this one. I'll just write it down once more so that you remember. If we don't have any external field, the first law is like this. External pressure. For reversible, it will be the internal pressure. Okay. This is for a closed system. So, and there are also other fields, obviously. So first of all, what is heat capacity? Let's just think like this. You can talk, obviously. I'm not the only person talking here.
Capacity is the amount of heat you need to put in to change the temperature.
By 1 degree, yes.
Yes.
So it's derivative, right? You can just write and desk CV.
Yeah.
Wait, I'll make it for you. Wait, I just don't put it next. Okay, should be now. Open.
So, and this is partial derivative of...
Yeah, it's the derivative of heat over
And-
temperature
And
at a constant volume.
Mm.
Yes. Okay.
So,
Well,
okay, so this is this expression, and this is the state function.
okay. I want to give you a small hint. What is heat? Well, volume is constant from the first law. At constant volume.
So it's internal energy.
Yeah, it's the change of internal energy, and the change of internal energy is a state function.
Okay, so then this.
It is also a state function because of this. Because there's only one way you can get one difference of energy in one permitted pathway.
Okay. So, but can you write this also like
The O over the T over constant constant volume. Exactly, you can do it.
okay? And
Yeah, okay, and this is your first law, exactly. You've done the first. And then the caloric state equation. The caloric state equation, I'll just quickly say it's U out of temperature. So it's U out of temperature and external variables equation. The caloric equation is the equation, so the caloric equation is the equation U equals U like a function of T and R1, R2, R. And you know that you can measure those sort of like CV, CP, etc. So why is it so easy to get this equation?
why is it so
Like experimentally, yeah, it's easy because like you know it's easy to measure heat capacity, right? Quite easy.
maybe
You just take your it's just a thing that we can measure amount of heat because we have like electric heaters and stuff.
Yeah.
So you can quite exactly measure how much heat you need for 1 degree because you can just stick a thermometer inside.
Okay,
And
so this is because it's easy to measure heat and temperature.
yeah. Well, it's not easy to measure heat. It's easy to measure how much energy we converted into heat.
Yeah.
And the external variables, you can just set them however you want to. Like I can just choose whatever volumes and just get a bunch of points. And then just we have some sort of a graph experimentally. Okay, that's about it on this part. And now, but yeah, we've done the first law and we only spent 1 hour to do it. Very nice. I hope the next one is faster. Okay, now the second law. So now we just talked how energy transfer proceeds, right? But I didn't say a word about what energy can transfer. So like what processes are allowed. And we do it using the second law. And the second law does this in quite an interesting way, which is called entropy. And now you hear the famous word, the famous phrase everyone states, the entropy of the universe always increases. You all heard it, like all of you have heard it, but probably none of you know what it actually means. So what do we say? We just say entropy is something that exists, and entropy exists in such a way so that for all spontaneous processes in an isolated system, the entropy has to increase. Okay, and now proving. Okay, so, well, first of all, universe is a giant isolated system, okay? Makes sense.
I made like diagram or
No, like here you can draw it if you want to, but there's no need. Like my proof is 2 lines of text. So let us think like this. So what happens eventually at any system?
it reaches
It reaches equilibrium. Okay, so when it reaches equilibrium, then can it have any more spontaneous processes?
no.
No, okay. So can its entropy decrease after it reached equilibrium? So so basically, when I get to some state, can my entropy decrease going further to equilibrium, or it has to increase in an isolated system? Yeah, it has to increase indeed. So like you have this some point. Oh, I'll just draw time and entropy. Right? There is this point, right? And look, for example, we know that equilibrium is somewhere. It can be either below, above, or at the same level, right? Okay, if it goes below, what does it mean? It means that the system spontaneously moves in a way that decreases entropy. Is it possible? So it cannot go this way. If the equilibrium state is above, it has to increase the entropy, right?
That hasn't reached.
Yeah, then it's not equilibrium. And if it just stops, then it's at equilibrium because it cannot go up spontaneously. So what can you say about this state of entropy because of this? Is it the minimum, maximum, or just some value?
It is maximum
Yeah.
because it can't increase.
Because it cannot increase and it cannot decrease. So it just stays indefinite, but it did increase before this value. Okay, yeah. So you see, proving is not scary. We didn't write a single mathematical symbol for this proof, which is quite fun actually. But now I'll talk about entropy of a more real state. So we just said, okay, entropy is something weird that exists, right? But I didn't say a single word how it exists, why it exists, for what reason it exists, right? It's kind of weird because for entropy to actually make some sense for us as scientists, we actually need to somehow quantify it with the real process, right? And now let's think like this. There is a system, just some system, which is isolated. So, and I just split it into 2 parts. Yeah. I'll call this alpha and beta. So each of them has their own entropy and their own internal energy. So we say that the total energy is U in alpha plus U in beta, right? And what is the total entropy of the system? It's the sum of entropies of parts, right? Okay, but because the system is isolated, what's the value of the total energy? Does it change over time? No, it's constant. Okay. And then we'll just say, okay, then let's say some amount of energy moves. Then obviously the U from A has to be minus the U from B. Do you understand why, right? Because the energy has to conserve. So if it goes away, it has to come here in the same amount. And now let's look what happens with the entropy. So there can be two cases. Our system has either reached equilibrium or it has not, right? But our system is in equilibrium. So if this transfer is allowed for energy, what happens with entropy? It's still in maximum, right? Makes sense, right? So in this process, the entropy change has to be zero. If it's allowed, even. And because we say the other variables are isolated, the only variable that can change from entropy can change from is internal energy, right? Makes sense, kinda. Yes? So we say, okay, then it has to somehow change from U alpha, the U alpha plus this one also makes sense, kind of. So this is how much changes from the first one, how much changes from the second one. But we know this one. So it's the U alpha, the S, the U alpha, the S, right? But the sign is the opposite one. U beta, right? It is zero, right? But did I say anything about the value of the O I chose? I did not. So this one has to be zero, right? Because either this or this has to be zero for this to be zero. So this concludes that you can look at your pages that the change of entropy over energy will be the same for both. So I'll have to do like this. I'm sorry for the people who are watching. So the S alpha over the U alpha has to be the same as the S beta U beta, right? And now let us think. If a system is not in equilibrium connected to A, so external forces, it has to be in thermal equilibrium, right? Because we didn't say any other process is allowed even. And which variable has to be the same for two parts of a system in thermal equilibrium?
Temperature.
Temperature, yes. So we say, wow, it's probably temperature. And now just to be convenient, we say that the S over the U equals 1 over T. The reason why we do it is because then the signs are convenient to work with. So that we say the U over the S is equal to the temperature. And we just say P is always greater than 0. It could have been the same if you choose the other sign, because we know that the internal energy has to increase. But we just choose the temperature to be greater than 0. It's just convenient. We just like positive numbers because you cannot lose a minus where there's no minus. Okay. And now some more proving. And again, I remind you that this only holds for a quasi-static process. Because remember when we said this part, we said that the system is in equilibrium. When the parts of the systems are not in equilibrium, this does not hold. So there's a temperature difference. So there's some waste heat that forms due to the temperature difference. And I think I kind of spoiled you the next proof. Yeah. Okay, who wants to prove? You're going to prove a lot today, you probably noticed it already.
The next one would be proved. I mean, it's just a science, right?
Yeah, it's just
It has to prove that the differential of
and we have to prove that the U over the T, the constant A is greater than 0. Wait, the U ds.
yes.
Okay. And I gave you a hint accidentally again. Right?
Yeah, since the U over this equals T and
Yeah.
T can never be negative.
Yeah. This is temperature. Okay. And now I suggest you to do a weird way. Let's try it like this. I don't know. You might remember the magic thing called chain rule. Sorry, I'll write it in a more convenient way. So there's the chain rule, which says you can do stuff like this. So I just say, okay, the U over the S is the same as the U over the T times the T over the S. I do like this. And now let's just look at parts. This is greater than 0, right? What can we say about this thing? Is it greater? Do we know the sign of this one? So we sometimes back then said it should be greater than 0, if you remember. So what has to be with this sign for the product to be greater than 0? This also needs to be greater than 0. Okay, yeah, this is the proof. That's everything about this proof. And the next one is Clausius inequality. But before we say Clausius inequality, I'll write an important thing called the fundamental theorem of thermodynamics. So it says that for the reversible process, now we know that heat difference is T delta S for a reversible process. So we can write that. So these are all the other fields we don't concern about because those are the ones we actually care in chemistry usually. Okay, so.
Why is the P delta V not in the
Hmm?
formula on the sheet on the A?
Because A is an external force also, like I'll just exclude that volume as something which like there's volume and there's the rest of external variables. But technically volume is also external.
Mm-hmm.
I'll just write it this way so that it's a bit more understandable. Why can I just dump the rest? Okay, the rest is Clausius inequality. Anyone heard about Clausius inequality? So the Clausius inequality says that for any process, where Q over T is less or equal than the S. Can you explain me why? So first of all, what can we say? We can say that the heat and the work are connected somehow, right? Well, you know how. So we say that in one case is just this, right? And which case is this? This is the reversible case. And in the irreversible case, it's Q ir plus the V ir, right? Okay, which one is greater, reversible or irreversible? Yeah. So this implies that the Q has to be less because the heat here is less also. Because for both cases, the delta entropy has to be the same. Entropy is the state function, right? But the heat here is less because work is more. So entropy has to be more for the same heat. And they're the same if it's reversible. Okay? So next one, third law. So because we already said that the entropy depends on heat, then we can just say because entropy, the S is this, the Q reversible over T, then we can also integrate it as well, right? So we say, okay, then we can integrate it from initial temperature to final temperature, which is S plus S of temperature plus constant. We don't know how much is the constant. Sad. But there is the thing called the third law of thermodynamics. It says this constant equals 0, just because. And for all chemicals is the same and it's 0. So because the integral from 0 to 0 is 0, for everything, entropy is the same value of 0 at the temperature of 0 degrees. This is why also any isothermal process does not change the entropy, because as long as this integral has to be 0, the change of entropy is the difference of those constants. It's the next proof. I'll just quit. So the difference of the constants has to be 0 because the constants are 0 themselves. So it doesn't change the entropy as long as it's reversible and isothermal, which is quite fun, to be fair. And also from this exact state, you can show that a temperature of 0 degrees cannot be reached in a finite amount of operations. From the U equals from this one. You just take the derivative over temperature, and you get that because the S over the T approaches 0, you just need to take increasingly more heat for an increasingly slow decrease in T. I'll not show it mathematically because no time, I'm sorry. So yeah, this is why. And now the part is actually chemical thermodynamics that I took 2 hours for an introduction, which is not nice. I'm sorry for this, but now I'll try to be a bit faster. And I will just ask you to try to do as much as you can at home for the proofs, which I skipped, because they are important for you to understand. But as of now, what do you understand about the laws of thermodynamics? So there is the first law, which says energy is conserved. There is the zeroth law, which says equilibrium exists and thermal equilibrium is equal temperature. There is the second law, which says if a system is isolated, the entropy has to increase. This is why we have the fundamental theorem of thermodynamics. And we have the third law, which no one uses. Yes. And now the question is, technically it's enough for all the thermodynamics. The question is, you have entropy as an external variable in the U, which is not nice. I don't like entropy. I cannot put 1 unit of entropy into a system. I can put energy, I can put temperature, I can put pressure, I can put volume, but I cannot put entropy. I really wish I could. This is why we actually introduce such a thing as thermodynamic state functions, also named characteristic functions. And the first one I will show is enthalpy is like this. So H equals U plus PV. Why is it important? When we take the differential, the D or PV, right? This is a product, so you can just expand it to the product. This is the U, and now we just expand this product. And what do we see? Those two canceled out. So what is the result? You see that we effectively just swapped pressure for volume as the independent variable, which is quite convenient actually. And also, well, just let's think like this. If the process happens at constant volume, then this is zero, right? And TdS is the only part that remains in the differential, and it corresponds to heat. So actually we say, okay, enthalpy change at constant pressure equals the heat in the process. And now you can remind yourself for your chemical reactions and the standard enthalpy. You see, you always say it is equal to the heat in the process and everything like this. Well, it is as long as pressure is constant, indeed equal to the heat, as we just showed it. So you see, chemistry begins to make sense at this point. Quite an interesting thing that I will not say right now is also fundamental equations. Why are fundamental equations nice? You can derive everything else from them. For example, this one, or you can read a bit more in the notes because I don't have a lot of time for this one. And also, now let's just think about the most painful part of the initial U. What is the most painful variable we have in thermodynamics?
Entropy?
Entropy, and we don't like entropy. We can swap, like, let's swap them. Why not? Then we can introduce something like this, which is Helmholtz energy. Let's quickly write down the differential. Okay, we've done it. We don't have entropy as an independent variable at this point. So we can use this somehow already. The question is how? If we talk about Helmholtz energy, we can first mention that, okay, there are also external works, right? We still do not forget they exist. And now we say, okay, when the process happens reversibly and at constant temperature, what happens with this one? This cancels out, right? And what remains? The only ones that remain are PDV and this part. And they are the total work that is performed by the system. So we magically show that at constant temperature conditions, the change of F actually responds to the energy the system can perform as work. This is also why this variable is called Helmholtz free energy, the energy that can be set free as work. And obviously, again, a small reminder, because for the reversible process, the work is the largest one. If it's not reversible, it's less. But this is the maximum value we can theoretically push out. And the other one is Gibbs energy, the one you like as chemists. We define it like this. Okay, can someone quickly say how I get this differential? It's the same, right? The K minus the S, and this was we know, right? And again, we don't forget this part. And now let's think, okay, and now we have a process, constant P and T. So which ones cancel out? Those two, right? And so what is the change of the Gibbs energy in this case, if it's reversible? It's all the other work, which is not your mechanical expansion and not heat. So Gibbs free energy is the value that corresponds to the work that is not the work which you can do by just physical means. So it's your chemical work. This is why we like Gibbs energy. Because we just showed that it is kind of the equivalent of your chemical work. Okay, as of now, does it make sense? And yeah, it gets interesting since now. Before that, it was kind of boring because it wasn't chemistry. Now it's chemistry. So, okay, as of now, we just did all 3.1 because I wrote all the proofs and it's apparently a lot faster when I write the proofs. And now the question is the sign. So it's a very famous saying that they say in schools, in like the first lesson, that the Gibbs energy sign equals the direction of the reaction. You've heard it at least once in like the first or the second class in like general chemistry, thermodynamics, all this stuff. The question is why? It's quite a reasonable question to have asked actually. And basically you can, first of all, I'll just quickly run a proof for you to show that it's actually fake. So now we'll make a small meme so that I'll show that at S where const, the sign of enthalpy is sufficient to say if a process is spontaneous. You probably don't believe me. Because like enthalpy, how is it connected? Okay, now let's write it down. So we have, well, first of all, a small prefix. So I'll draw an isolated system out of two parts. And there can be some work done, so there can be V transferred at the condition that S and P in this part are constant. Right? Does it make sense? Like, okay, I just want you to understand the setup before I do the maths. And now let us think. So the enthalpy change, what does it equal to? It is the heat of the process, right? Well, at constant volume, right? At constant. And now let us think. How much heat do we have at constant entropy from external? Zero. Yes. But we say if delta H somehow apparently is less than zero, then this has to be less than zero. Apparently, somehow. But how? And now we use the Clausius inequality, which says that this heat, which is the H, has to be greater or equal than TdS. And it is only equal to TdS in the case the process is reversible. You remember this, right? And now we say, okay, so no heat got transferred, but in this part of the system, if the process proceeds with negative enthalpy, somehow entropy is generated, right? It increases because this is zero. So if it's less than zero, then this has to be greater than zero for obvious reasons. What happens? Wait, sign, right? No, sign is correct. Yeah, okay. So you have entropy being generated in a part of an isolated system. So in the isolated system, in general, it is also generated. So the entropy of the isolated system as a total has increased in such a process where the sign of enthalpy is, I'm stupid. I'm sorry. Mind my stupidity. So you see, we have just generated entropy out of nothing. So it's spontaneous. So thermodynamics likes this thing because second law. And we just showed that the sign of enthalpy is actually totally enough to show that the reaction is spontaneous at those conditions. And now I can just say you can do it because I will not prove it. But the same applies for F at constant Tv and G at constant Tv. Same applies. So in such conditions, they reach the minimum. So if all external, so basically if all the variables in the differential for a reversible process are zero, but the change of the potential is still negative, so that there should be something that generates this external entropy for an irreversible process. This is why it's spontaneous. Okay, does it make sense?
Yeah.
Okay. So you see, we just magically showed that your chemistry works because those boring laws. And there are cases where it works. And I'll just quickly say about the chemical potential. So before that, we just said there's some magic external variable. And now let's just call it M, which is the amount of substance. And energy somehow changes because of it, right? So we'll define the chemical potential as for a chemical. Well, all the rest are constant, which is also the same as also makes sense why, right? Okay. So I'll just show you a simple, easy proof. Let's say there's only one chemical. So the only variables we have are P, and M. What is the total Gibbs energy? It's N times G molar, right? You know why, right? Okay, now let's just calculate. Mu I equals Z over Z N times G molar. The question is, does molar Gibbs energy depend on moles of the one compound? It doesn't. It only depends on those two. So you see, we just converted the extensive Gibbs into the intensive molar Gibbs. Noted somewhere. So yeah, it just equals G molar. And now the sad part is when there are more than one. Because it gets sad at this point. Why it gets sad? Because chemicals tend to interact with each other. So when you take this derivative, G molar will itself depend on molar fractions. I wanna cry. You probably also wanna cry. You can look at the lecture notes and see the math on page 13, where I show how I actually derive it and I get this scary formula in the middle. So you see, it's a bit hard to simplify. And I will not simplify it today, but you can read the book I cited, which is Barshevsky, Chemical and General Thermodynamics. He does simplify it in chapter 9. So, yeah, obviously, to understand what he does in chapter 9, you have to first read chapters 1 to 8, which is like 300 pages of math. But if you do it, congratulations, you actually understand physics. But I'll just define some magic variable called partial molar Gibbs energy for an chemical. And I defined it in such a way that it is equal the d of G total over d and I. And to add on top of that, it is also equal in such a way so that G times Ni. I just say it is this way. I will not prove it, although I can, but I will not because it will take another 2 hours. So we stopped at showing about partial molar quantities, and now I'll just say that chemical potential is the partial molar Gibbs energy because it is. You can actually prove it, but if we prove it completely, it's gonna take another 2 hours, which is why I'm not going to prove it. Although you can see a bit of explanations in the notes about the maths, how it is behind it, and again, you can read the book. But because we say that chemical potential is defined like this, the Ga total, and we then say that Ga total equals Ne times mu E summed up. So like this formula is just the definition. This formula, you need to derive it. We just say it is, so I'll not derive it today. And then from here, we can just do some maths, or easy maths. So we can say Ni equals molar fraction times total amount, right? And we can write it down like this. You see what I've done, right? And then I just divide and get K molar. Also quite simple stuff. You can derive it yourself. I think it was one of the questions for exercises. Yeah, and then we talk about how it behaves over time. And now we have to introduce such a bad thing called chemical activity, which is totally hated by everyone who invented it, especially because they could not decide how to invent it so that it works. Say that the Gibbs energy equals what? VDP minus SDT, right? This one we'll ignore because we're doing it at isothermal conditions. And now, ideal gas. What is volume of ideal gas expressed over pressure? PV equals nRT. V equals nRT divided by P. Okay, then we get dG equals nRT dP over P. From here we get G equals nRT logarithm P plus some constant, right? Well, if we integrate. And now we introduce the thing called standard state. Why do we like standard states? Because they get rid of the plus C. And we just choose standard pressure to be 1 bar. So that it then turns out to be nRT log P over P standard. Magic. So this is the idea of how we come up to chemical potential and activity. We say, okay, we have a solution with some solvent, and we say, okay, let's just assume it's a very good solution, and it's such a good solution so that the Gibbs energy of the vapor is the same as of the ideal gas. It's very convenient for us. This is called Raoult's law, which is a law of activity of pressure dependence over the molar fraction, which we just say works this way. Again, as too many things in chemical thermodynamics because the science does not make a lot of sense. And then we say, okay, let's think about the solvent or this solid in the solvent. Even if we change the amount of the solvent or some other compound in the solvent, if we have like 100% solvent or 99% solvent, how much will the chemical properties of the solvent change? Not really. So we can just ignore their activity. Say it didn't change compared to standard. So we say activity is, this is why activity is just 1. And now let's look at this one, right? This case, we see that, this one looks kind of nice, but chemical activity is quite convenient to be correlated with ideal gases. If it's a real gas, we can just somehow do some magic with the pressure so that it matches up. If it's dissolved, we can correlate it with vapor pressure. We like ideal gases. It's convenient. This is why we just invent activity such in a way so that the chemical potential is chemical potential at standard conditions plus Ft log A. So we just say that activity is such a quantity that the energy corresponds with the ideal one. It's just a small way to patch up the holes in the fact that we begin from ideal gases and just build from this. But yeah, it does not make any sense because because it should not make sense, let's say like this. Yes, and now we're going to the scary part, chemical reactions. The actually scary part. So first of all, let's just write a chemical reaction in a very interesting manner. I'll just write A1, V2, A2, K, N, A, N. So yeah, it's just generally I just wrote this reaction in such a way. And now I'll just say, okay, sure. Let me quickly take the equation. It's a mathematical equation, right? Let's just put it on one side. So this is the same as this expression. So V is the stoichiometric coefficient, and important things to note. For the sides on the left, it has a negative sign. On the right, it has a positive sign. A is just chemical. Okay, and now a brief question to be asked. What is the, now we're talking about some reaction mixture. How can we explain how much the composition of the reaction mixture has changed?
Change of volume, temperature.
Yeah, but we get, like, imagine we have some conditions and we just leave those conditions constant. Well, usually it's temperature and pressure because chemical potential. Because chemical potential is already equal to Gibbs, so it's convenient. So we just say that, okay, the molar Gibbs energy of the reaction mixture is equal to Gibbs energies of everything inside, right? Makes sense why. And remember, we defined Gibbs energy as being potential times moles and all summed up. Because we said chemical potential is defined this way. So we just say G reaction mixture equals the sum of all mu times all n at the given composition of reaction mixture. So this is at given n composition. And now assume the reaction is, now assume the total n constant. So the reaction can somehow proceed according to this equation, right? So some chemicals are converted into some other. But we need to somehow quantify it. This is why we introduce extent. This is extent. Extent. So you maybe remember from like the 8th grade chemistry lessons where you have like stoichiometry and you have to divide all moles by the coefficients to get like this proportionality constant, and you just figure it out. So this is this, but in thermodynamics. So we just define it such a way so that the n is like this. So we say extent changes the moles proportionally to the coefficients. Okay? And now let us think like this. If these conditions are true, which is the only other variable that can affect the energy of the reaction mixture. If all the other variables in Gibbs are constant. We're not talking about external right now. We'll talk about electrochemistry in 10 minutes. Maybe, if you have time. So, extent is the only variable that's left, right? Makes sense. Yes? So it has to, so what happens to the reaction mixtures Gibbs energy at equilibrium, at chemical equilibrium?
Nothing.
It's minimal. It's minimal because at not equilibrium composition, at constant temperature and pressure, it will try to somehow get into a state with a minimal Gibbs energy. So we can say, okay, this is, and so we say this one should be the equilibrium composition. So we say, okay, constant step pi and total n. Does it make sense why now, right? And now let's write what is, and now let's just plug this one here. So it is same as 0 equals to the sum of chemical potential, but chemical potential does not depend on reaction extent, right? They're the same at the same conditions. They only depend on the other things. But Ni is quite a different story. So it's the Ni over this one. And now we just say that the Ni is this one. So the epsilon is the Ni over the mu I. Okay, and this one is 0. And now we can simplify because this one is 1, right? And this one just goes on the top. So we end up that okay, this one makes sense somehow. So I say, okay, at equilibrium, there's chemical equilibrium. So this one has to be 0. And then we need to somehow quantify how much it changes at a given composition. So this is why we define the reaction gives energy, which is totally not the thing you would expect it to be defined as. Because the reaction gives energy is defined as reaction delta erga. It's defined as like this. So this is so this basically means for 1 mole of extent, what is the difference between the minimum and right now? Makes sense. And we can also give the same for standard condition. Okay, and now we just quickly do the chemical formula from the paper, which is, I'll just subtract this one from this one. And I get, okay, what do I have here? This one cancels out, and those one become one sum, because the stoichiometric coefficients don't change, right? And this is mu now. Okay, and now we remember that the change from standard is somehow connected to activity, right? You remember this? Yes? Okay, and how is it connected to activity? Yeah, Husserl ln activity. And you see those ones cancel out. So we end up that delta Rg equals delta Rg naught plus sum for all our k components mu I times Rt ln I, right? And now let's say, okay, this one can go here, right? Because it's log properties. And Rt is the same for all, so I can get it outside. So it's the same as plus Rt ln I to the power v. Makes sense, right? But what is the sum of logarithms? It's the logarithm of the product, right? So it's the same as but this is called the reaction quotient. So it's all the activities for the products. This is plus sign, so it's on the top. If the exponent is negative, it goes on the bottom of the fraction. So it becomes the Q. And magically, we get this formula from the equation sheet, which is like one of the two formulas you actually memorized. And the second formula, so let's just think what happens in equilibrium. What is the value of this thing, delta erga?
0.
0. Okay, and what does it physically signify?
There is no change.
No, the value of delta. It is the derivative. So you see, it's how much the energy changes with extent. The thing it is not the Gibbs energy of the mixture. It is the derivative, which is the thing almost nobody teaches. So this is 0. So we get 0 equals delta R G naught plus RT ln Q equilibrium. And how do we call Q at equilibrium? Equilibrium constant. So we get, from this we get okay. This is chemical part. Electrochemical. Do you want to stay for 5 or 10 more minutes or you want to go? If yes, I don't mind. You can just do electrochemistry on your own if you want to.
I think we can do it on our own.
Okay, just you can quickly have a look now and just say. And you know what? Because I skipped all the proofs, I'll just also ask you, same as the Latvian team, just please. The proofs you didn't have time to do them and send them to me if you want me to check. I suggest you to send, but yes, I'm sorry for not having enough time. And so yes, and tomorrow you're going to do this in the morning, and it's gonna be like a fake IChO exam. We decided with a lot, so we're going to solve them, and then probably I will grade them during lunch. And then during the tutorial, I prepared some questions on physical chemistry from the past year international Olympiads mainly, and one from Baltic. We'll also do them because you've already done preparatory problems. But yes, this is the proof at least that you need to know for the chemistry. So I think more words about thermodynamics before we end. So I hope you enjoyed the lecture. It was at least useful for you in some way. You understood that you didn't understand something before. Yes, you see that because it's so abstract, we can just get specific cases quite easily from some weird introductory points, but who cares about them? And it's generally the only thing that you will concern about. So you should at least know the second law for this year's advanced topics because it was mentioned like 5 times. So you just remember the total entropy, the state functions, which one to choose when. Read again if you have issues. And also you need to remember the reaction Gibbs energy. That is not the Gibbs energy of the reaction mixture. It is the derivative with respect to extent. So we just show that if the, so for, I'll just quickly mention one more thing. So if this thing is negative, it means that with increasing reaction extent, the reaction mixture's Gibbs energy is going to decrease, right? This is why if the at a given composition, this one is less than 0, increasing the reaction, pushing forward, so increasing the extent will push the reaction towards equilibrium. This is why it shifts to the right and proceeds forward. The same will go backward. If this sign is more than 0, then it will work the other way. The Gibbs will decrease if you decrease the extent. So the reaction will proceed backwards to decrease the energy of the reaction mixture. Again, remember it is at constant pressure and temperature. If you have, for example, constant volume and temperature, you would have used Helmholtz energy instead. If you do like in preparatory problem 7, if you remember, it was for a constant isolated system. Which one should you should have used instead of G in this case?
Kiloploids.
Isolated. You have U and V. Sorry, you have U and V constant. Isolated. So you have to use entropy of that isolated system because it's the second law. Second law says, okay, if you have isolated system, the equilibrium entropy reaches the maximum, not the minimum. Just another important thing. All those ones reach minimum, entropy reaches maximum. Yeah, and again, I'm sorry for the people who are watching mainly for having skipped out of half of the proofs in the second part of the lecture because we didn't have a lot of time. But yeah, anyone has any questions?
Really?
Not really. Okay.